students, welcome to today's video. So in the previous video we had discussed about the some of the important compounds of sodium, and today in this video we'll discuss the group 2 elements of S block, that is group 2 elements, and it is called as alkaline earth metals. Okay, so this group 2 elements, it comprise of beryllium, magnesium, calcium, strontium, barium and radium. So these are the elements of group 2, and they follow alkali metals in the periodic table, that is they are just after the alkali metals. Okay, so except beryllium, others are known as alkaline earth metals. Beryllium is not called an alkaline earth metal because it differs from the rest of the members, and because its character, that is its properties, it differs from the rest of the members of that group, and it shows diagonal relationship to aluminum, which we had already discussed. Okay, now we'll discuss some of the properties of this alkaline earth metals. Now the first one is electronic configuration. So these elements, they have only 2 electrons in the s orbital of the valence shell. So their general electronic configuration will be represented as noble gas ns2. You can see here, this is the electronic configuration of beryllium, magnesium, calcium, strontium, barium and radium. You can see the what is the last outermost electronic configuration. You can see 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. So it is actually ns2, that is noble gas ns2 is the outermost electronic configuration of alkaline earth metals. Now we'll discuss the atomic and ionic radii. So the atomic and ionic radii of the alkaline earth metals, they are smaller than those of the corresponding alkali metals in the same period. That is, you know that atomic and ionic radii, when you consider across a period, it will decrease, isn't it? So when it is compared to alkali metals, the size of alkaline earth metals will be little more lesser, that is little more smaller. So their atomic and ionic radii, it is smaller than the alkali metals. And down the group, you know that within the group, the atomic and ionic radii, it will increase because of the increase in atomic number, that is the number of shells will increase, so the atomic size will increase. So across the period, because of the nuclear charge, the size will decrease, and down the group, as the shells increases, the size will increase. Now we'll discuss the ionization enthalpy. So the alkaline earth metals, they have low ionization enthalpy. You know that because of the larger size, somewhat a larger size than the corresponding elements of the that period, it has a little more bigger size. So because of that, it is very easy to remove an outermost electron, so the ionization enthalpy will be less. Okay, so they have low ionization enthalpy due to fairly large size of the atoms, and since the atomic size increases down the group, the ionization enthalpy decreases. So down the group, as the shells increases, atomic size will increase, so it is very easy to remove an electron from the outermost orbital, so the ionization enthalpy a little more lesser. Okay, so that is all about ionization enthalpy. Now we'll discuss hydration enthalpy. So like alkali metal ions, the hydration enthalpies of alkaline earth metals ions also decreases with increase in ionic size. That is, as the ionic size increases, their hydration enthalpy decreases, isn't it? It is inversely proportional. That is, hydration enthalpy, it will decrease when the ionic size increases. So if we consider that, then beryllium, that is Be2 plus, it is having the bigger size, isn't it? Beryllium, no, it is having the smaller size. When come from down the group, if you consider, beryllium is having the smaller size, isn't it? So when the size is small, hydration enthalpy will be more, isn't it? It is inversely proportional. So Be2 plus will be having higher hydration enthalpy, then comes magnesium Mg2 plus, then calcium Ca2 plus, then Sr2 plus, and Ba2 plus. So this is the order of hydration enthalpy, that is beryllium is having the highest hydration enthalpy since it is having the smaller size. It is inversely proportional. Now we'll discuss some of the physical properties of alkaline earth metals. So it is a silvery white, lustrous and relatively soft but harder than the alkali metals. So these elements, they are silvery white, lustrous, that is shining, and it is relatively soft but harder than the alkali metals. When compared to alkali metals, they are harder but they are relatively soft metals, and their melting and boiling points, it is higher than the corresponding alkali metals due to their smaller sizes. When compared to alkali metals, their sizes are smaller, isn't it? So they are having what do you say, melting and boiling point, it is a little more higher. So they are strongly electropositive in nature. Okay, so then calcium, strontium and barium, they impart characteristic brick red, crimson and apple green colors respectively to the flame, because I have already explained that in the flame what happens is the electrons, they are excited to the higher energy levels, and when they drop back to the ground state, energy is emitted in the form of visible light and they will get a particular color. Okay, now this beryllium and magnesium, they are strongly bound to get excited by flame, that is their bonds are strong so they won't get excited. Okay, so they don't impart any color to the flame. So this calcium, strontium and barium, you can detect it using a flame test qualitatively, okay, or by flame photometry, anything. Now these alkaline earth metals, like those of alkali metals, they have high electrical and thermal conductivities, which are typical characteristics of metals. Now we'll discuss some of the chemical, actually we're not discussing the chemical properties of alkaline earth metals. They are comparatively they are less reactive than the alkali metals, because their outermost electronic configuration is ns2. In for alkali metals it is ns1. It is what to say, they will remove they have a tendency to lose that electrons easily than alkaline earth metals. So this alkaline earth metals, they are less reactive than the alkali metals. Okay, so some of the reactions of this alkaline earth metals, that is reactivity towards air and water, reactivity towards the halogens, reactivity towards hydrogen, reactivity towards acids and reducing nature, solutions in liquid ammonia. Some reactions is given in your textbook, you can go through that reactions. Then we'll discuss some anomalous properties of beryllium. So I have already said that the first element of group 1 and group 2, both they have different properties, that is they have some different kind of properties from the remaining elements, isn't it? So we'll discuss some of the different properties of beryllium, that is beryllium is the first element of group 2. So beryllium, they has exceptionally small atomic and ionic sizes, and thus does not compare well with other members of the group. Because of high ionization enthalpy and small size, it forms compounds which are largely covalent and get easily hydrolyzed. Okay, so they have high ionization enthalpy because of smaller size, a little more. So beryllium does not exhibit coordination number more than 4, as in its valence shell there are only 4 orbitals. So the remaining members of the group can have a coordination number of 6 by making use of d orbitals. Beryllium does not have d orbitals, so since it has only 4 electrons in the valence shell, it can form a coordination number of only 4. Then the oxide and hydroxide of beryllium, unlike the hydroxides of other elements in the group, are amphoteric in nature. Okay, so the oxides and hydroxides of beryllium, they are amphoteric in nature, because that is they can act both as an acid and base. Now we'll discuss some important compounds of calcium. Okay, so the important compounds of calcium, that is industrially important compounds of calcium, they include calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate and cement. Okay, so we'll discuss about these compounds now. Now the first one is calcium oxide, or it is also called as quicklime, and the formula is CaO, calcium oxide. Okay, so the calcium oxide or the quicklime, it is prepared on a commercial scale by heating limestone, that is calcium carbonate CaCO3, in a rotary kiln at 1070 to 1270 Kelvin. So this is the image of a rotary kiln. So in this the limestone is heated. Now this is the equation, that is calcium carbonate CaCO3, that is limestone. When it is heated, you will get calcium oxide, that is quicklime, plus carbon dioxide. So this is the preparation of calcium oxide. So this calcium oxide, it is used in the manufacture of sodium carbonate from caustic soda. It is employed in the purification of sugar and the manufacture of dye, stuffs, all those. Okay, now we'll discuss the second compound, that is calcium hydroxide, and it is also called as slaked lime, that is CaOH twice. Calcium hydroxide, slaked lime. So this calcium hydroxide, it is prepared by adding water to quicklime, that is calcium oxide is quicklime. So when you add water to quicklime, you will get slaked lime, that is calcium hydroxide. Okay, so this calcium hydroxide, it is also called as milk of lime, that is its uh, aqueous form. That is when this calcium hydroxide, when it is mixed in water, you will get a suspension of slaked lime, and that is called as milk of lime. So when this milk of lime, when it reacts with chlorine, okay, that is calcium hydroxide, that milk of lime, that is aqueous solution, when it is mixed with water, when it reacts with chlorine, you will get a hypochlorite, a constituent of bleaching powder. Okay, so you'll get a hypochlorite here. Fine. So this calcium hydroxide, it is used in the preparation of mortar, building material. Then it is used in whitewash due to its disinfectant nature, all those. Okay, now the next compound is calcium carbonate, that is CaCO3. So calcium carbonate, it occurs in nature in several forms like limestone, chalk, marble, etc. So it is prepared by passing carbon dioxide through slaked lime, or by the addition of sodium carbonate to calcium chloride. So there are two ways of preparation. One is either you have to pass carbon dioxide to calcium hydroxide, that is slaked lime, you will get calcium carbonate and water molecules. Or another way is by the addition of sodium carbonate, Na2CO3, sodium carbonate to calcium chloride, you will get calcium carbonate plus sodium chloride. Okay, so these are the two ways for the preparation of calcium carbonate. Now the next compound is calcium sulfate, and that is also called as plaster of Paris. I know that you would have heard that name before, plaster of Paris, isn't it? So it is its formula is CaSO4 half H2O. Okay, that is plaster of Paris calcium sulfate. So it is a hemihydrate of calcium sulfate. That is this plaster of Paris, it is obtained from gypsum. Okay, so gypsum, that is calcium sulfate CaSO4, 2H2O, two molecules of water, it is called as gypsum. Okay, CaSO4, 2H2O is gypsum. So that gypsum, when it is heated to 393 Kelvin, you will get calcium sulfate of what we call as plaster of Paris, that is half H2O. So this is the reaction, that is calcium sulfate to H2O, that is gypsum. When it is heated, you will get CaSO4 H2O, that is half H2O plus 3 H2O. So this is called as plaster of Paris, or this calcium sulfate which is formed in this reaction, it is also known as dead burnt plaster. Okay, that is also called as dead burnt plaster. So it has a remarkable property of setting with water. So on mixing with an appropriate amount of water, it forms a what is a plastic mass that gets into a hard solid in 5 to 15 minutes. Okay, so you know the variety of uses of plaster of Paris, isn't it? It is used in building industries as a plasters, and it is used for immobilizing the affected part of organ when we get fractured or something with leg or hands. We'll use plaster of Paris so that that organ is not moved for that. So then it is also used for dentistry, then or in ornamental work, and for building statues, all those, etc. So these are the uses of plaster of Paris. Now the last compound is cement. So cement, it is an important building material, you know that, isn't it? So cement, the raw materials for the manufacture of cement, they are limestone and clay. So limestone and clay are the raw materials of raw materials for the manufacture of cement. So what you have to do is, when clay and this limestone, okay, when lime and clay, they are strongly heated together, you have to heat them both together. What happens is, when they are heated, they fuse and react to form cement clinker. Okay, so this clay and limestone, when it is heated together, they will fuse and they will form cement clinker. Okay, so this cement clinker, okay, what you have to do is, it is mixed with 2 to 3% of gypsum. To this cement clinker, mix 2 to 3% of by weight of gypsum, that is CaSO4 2H2O, and you will get cement. Okay, so what you have to do is, limestone and clay, you have to heat it strongly together, they will fuse and they will give you cement clinker. To this cement clinker, add 2 to 3% by weight of gypsum, you will get cement. So this is how you form cement. Now you know that cement, when it is mixed with water, the setting of cement, it takes place to give a hard mass, isn't it? When mixed with water, the cement, it will set to give a hard mass, like you can see in the image. Okay, so this is due to the hydration of the molecules of the constituents and their rearrangement. Now here we are adding gypsum. The purpose of adding gypsum is just to slow down the process of setting of the cement so that it gets sufficiently hardened. So you know the uses of cement, right? So cement, it is used in concrete and reinforced concrete, in plastering, and in the construction of bridges, dams, and buildings. All kinds of constructions we use cements. Okay, so with this we had completed the S block elements. Even the chapter is done. So with this video we have almost covered all the important topics of first year. Thank you.